ReLU, or the rectified linear unit, is becoming one of the most commonly used, if not the default activation function for many types of neural networks, such as feed-forward neural networks and convolution neural networks, because models that uses them are generally easier to train and achieve better performance. So let's talk about ReLU, some of its properties, some of the shortcomings of the sigmoid that ReLU is able to manage. So let's get into it. Alright, so this is how the ReLU function looks like. It's this red line here. The blue line is the gradient of the ReLU. We will talk about it later. But the ReLU line is a piecewise linear function. It has a minimum of 0, and it goes all the way up to infinity, and therefore it's always positive. Another interesting property of the ReLU, actually the ReLU, the function itself, I'll call it R, is equal to max. It's a very simple function, just the max of 0 and the input. I'll call the input z. So if you have a neural network, these are your inputs. You will pass them into a linear layer, and then you put it through a ReLU, W transpose X, right? So these are your input, X1, X2, Xn, right? And then you do linear transformation, W transpose X, and then you pass that to the ReLU. If that, we'll call this Z. So ReLU just simply looks at your Z vector, and it sees if the Z is greater than 0, it will keep it as it is. If it's less than 0, it will just suppress it to 0. So for example, if your Z vector looks something like this, 10, 3, minus 1, minus 2, minus 2. This is your Z vector, the output of W transpose X. You pass that to the ReLU. The ReLU will generate another vector, 10, 3, 0, 0. So it will simply look at element by element, because ReLU is an element-wise function. Basically, an element-wise function is a function that applies to each element of the vector in the same way. So ReLU of Z, ReLU of vector Z is the same as ReLU of Z1, ReLU of Z2, and so on. So when you apply ReLU to vector Z, it's like you're applying, it literally looks something like this. So ReLU of Z is equal to ReLU of Z1, which is max of 0 and 10, and max, see, it applies element-wise to each element of the vector, and so on, max of 0 and minus 2. And therefore, so max of 0 and 10 is 10, max of 0 and 3 is 3, max of 0 and negative 1 is 0, max of 0 and negative 2 is 0. So this is how the ReLU function works. It's an element-wise function, applies to each element of the input independently. All right. So another property, and a very important property of the ReLU, and this is why actually ReLU has become very, very famous in deep learning as an activation function, is that it overcomes one of the major shortfalls of the sigmoid, and actually the tanh function as well, which is that the function saturates at both ends, and the function has a vanishing gradient. So let's talk about both. First of all, what do I mean by the function saturates at both ends? If you look at the sigmoid function here, if you see, what is the sigmoid of 5 and the sigmoid of 10? Sigmoid of 5 and sigmoid of 10. Actually, the sigmoid of 5, if you look at it, let me actually drag this here because it's not visible. Yep. Okay, so what is the sigmoid of 5? It's something like this, very close to 1. Sigmoid of 10, again, very close to 1. So the problem with the sigmoid is that sigmoid of something like 5 and sigmoid of 10 are almost the same, right? And likewise, on the other end, sigmoid of minus 5 and is very close to sigmoid of, negative 20 or negative 10. So the sigmoid almost snaps to 1 and to 0, right? So it doesn't matter how different your input is, the sigmoid will almost return the same value. All the fun in the sigmoid happens around its center point, around the 0. This is where all the fun happens because it's almost linear here. And yeah, so the ReLU function overcomes that because the ReLU function has no saturation, right? The ReLU function just keeps on going. It's just the maximum of 0 and x. It's a simple linear function on the positive end here, and just 0 on the other side, so it has no saturation. another interesting property of the ReLU and why it has overtaken the sigmoid function. This is actually much more important, which is that if you look at the derivative of the sigmoid function here, this orange line, you'll see that it approaches 0 at the tails here, right? At both ends. So the derivative of the sigmoid, if you get a score of 5, 7, or 10, is almost 0. And if you get a score very negative number, like -7, -10, the derivative is almost 0 as well. So you have a problem where your derivatives are approaching 0. So the derivative of the output with respect to the input, will be 0. So when you're doing gradient descent, you'll be multiplying gradients with each other from the chain rule. You'll be multiplying this gradient with all the upstream gradients until now. So if this gradient is 0, it just zeroes out all of the upstream gradients, and it means that when you're doing stochastic gradient descent and you want to take a step in the direction of the minimum, your step size will be 0 because your gradient is 0. So it means your model will not be learning anything. It's just every iteration it's taking a step size of 0, and it's not moving anywhere. It's not learning. So if you look at the gradient of the ReLU, which is this, very simple function, you'll see that it does not saturate. It does not reach, especially in the positive end, it's almost 1. Why? Why is it 1? Because we said ReLU returns x if x is greater than or equal 0, and returns 0 otherwise, right? It's simply the max of 0 and x. So it returns x if x is greater than 0 and returns 0 otherwise. So what is the derivative of the ReLU? I'll call it r prime. It's simply what's the derivative of x with respect to x is 1, and derivative of 0 is 0. So it's 1 if x is greater than 0 and 0 otherwise, right? So on the positive end of the ReLU, its derivative is always 1. So if we go back to our example on the ReLU, you have that's your ReLU function, and this is your input. So if you take the derivative, it will be something like 1, 1, 0, 0, right? So at least for those two elements, it will not be 0. But ReLU also has a problem, which is it's on the negative end. If it gets an input which is negative, it will return 0. So there is another problem with ReLU. It's called dead ReLU. Dead ReLU, it means if your inputs are the inputs that keep on coming to your, let's say that this is your layer here in the neural network, we'll call this layer H. The output is H, and the input is H, let's call this HL, and this is HL minus 1, and this is your ReLU. So if your input that's coming to your ReLU activation function is always negative, your output will always be 0. And this is a situation that we call dead ReLU, which means your ReLU is always outputting 0. So again, your model is not learning anything. The hope here is that your inputs will not be just connected to one ReLU. You'll have like a multi-layer perceptron here, and you'll have multiple inputs. Your input will be connected to all of them. So hopefully some of the other ReLUs will return a positive number, and it will force your input to, when you do backpropagation, your input will become positive, and therefore the ReLU that used to generate a 0 will now start to generate positive numbers as well. But to overcome this vanishing gradient, dead ReLU problem, some researchers have developed another activation function that's called the leaky ReLU. So this is how the leaky ReLU function looks like. It's very similar to the ReLU function. It's this yellow dotted line here, very similar to the ReLU function on the positive end. So leaky ReLU is equal to max of, so the ReLU was the max of 0 and x, right? Maximum of 0 and the input. The leaky ReLU is maximum of the input and alpha times input, okay? And this alpha is a hyperparameter that controls the slope of the negative end here. So it's just a hyperparameter that your model can learn with gradient descent, and it's a controllable parameter. And this is always a good idea. Like if you If you want your model to be more flexible, add a hyperparameter and your model will use it and find the optimal value for that hyperparameter. So this is helpful because on the positive end, your ReLU does not vanish, and also on the negative end, your ReLU is no longer 0. So the gradient of the ReLU, as you can see, this blue line here is 1 and it's not 0 anymore, right? So we've overcome the problem of the dead ReLU. That's it. So that is the ReLU function is simply max of 0 and the input. Leaky ReLU is max of alpha times the input and the input. And leaky ReLU overcomes one of the shortfalls of the ReLU is that it has what is called the dead ReLU, where the ReLU is always 0. The gradient of the ReLU is always 0 on the negative end. So the gradient just dies. So to overcome that, we can use a leaky ReLU that has where it has a slope on the negative end, and therefore its gradient is not 0. And both ReLU and leaky ReLU overcome the shortcomings of the sigmoid and the tanh function of the saturation on both ends and that vanishing, especially the vanishing gradient problem. So that's it. Maybe one last remark is that ReLU is not used that much in recurrent neural networks. Tanh and sigmoid are still the most commonly used functions there. We're gonna come talk about that later, why that is the case. It has something to do with exploding gradients and gradient clipping. We will talk about that later, but until then, hope you enjoyed the video. Don't forget to like and subscribe, and see you in the next video.